Hi everyone, let's talk about the general version of Bézout's lemma. This is a lemma from number theory, and in essence what it does is that it looks at the relationships between three kinds of objects. One is the linear combination of an n-tuple of integers. The second is the common divisors of this n-tuple of integers. And the third is the greatest common divisor of this n-tuple of integers. And what Bézout's lemma in its general form does is that it establishes relationships between these three entities. So here's what we're going to do. We're going to let there be three kinds of things. So the first is t, which is equal to a1, a2, all the way through to an. And this is going to be an n-tuple of integers such that they're not all 0. So we're excluding the possibility that a1 through an are all 0. Secondly, we're going to have the set D, which is equal to the set of linear combinations a1, x1, all the way through to an, xn, such that x1 through to xn is any n-tuple of integers. And finally, we're going to say d is equal to little d is equal to GCD of a1, a2, all the way through to an. So these are three definitions that we're going to need several times. So here's what Bézout's lemma in its most general form says. First of all, it says that the minimum of the set D restricted to its positive elements is equal to, well, first of all, it exists, and we can know that it exists by a fairly simple argument. We just take one of the non-zero elements and we give it a coefficient of itself, but I won't get into the proof right now. So the minimum of D intersects Z plus exists and equals D, which is equal to the GCD of T. T is this n-tuple of integers. So the smallest positive linear combination is equal to the greatest common divisor. Secondly, if we have an integer k, such that k divides a1, k divides a2, all the way through to k divides an, so k is a common divisor of t. This is true if and only if k divides GCD a1 all the way through to an, which is equal to d. So there is a one-to-one correspondence between common divisors of t and the divisors of the greatest common divisor of t. And thirdly, we find that an integer m is equal to a linear combination a1 x1 plus a2 x2 all the way through to an xn if and only if m is a multiple of d. So d has to divide m. So these three components together make Bézout's lemma. And they might seem like they're different things, but there's actually a very nice way of looking at this. We'll look at the number line. In particular, we'll look at the positive number line. So let's say we have 0 over here, so this is 0, and we have d here. We have 2d and 3d and 4d and so on. What we have is that, and remember, little d is the greatest common divisor of the n-tuple t. So this over here is, by this statement, equal to min of d intersects z plus, capital D. And what we have is that we have elements here, these integers that divide d. So if k divides d, then we have the common divisors here. So this is where the common divisors are. And if you look at this part over here, then these integers, the multiples of the greatest common divisor, they're equal to all other linear combinations. So the number line is divided into three parts. One is this, which is between 0 and d. One is d itself, and the rest is the multiples of d. So that is how I would visualize Bézout's lemma. And I just want to mention one more thing, which has to do with the LCM. And the LCM, it turns out, this is a bit of a bonus, but the proof is very similar. A number is a common multiple of t, and this is assuming all the elements of t are non-zero, otherwise we can't speak of common multiples. This is true if and only if it is a multiple of LCM of t. So we have a very similar result in this case. If a number is a common multiple of t, then it's a multiple of the LCM of t. And if it's a multiple of the LCM of t, then it is a common multiple of t. Thanks for watching, and I'll see you next time.